Welcome to our first coronavirus seminar of 2020. Very likely not our last. I'm very happy that Daniel has kindly agreed to experiment here with Zoom. I think something a number of us have done before. I think it should work just great, and hopefully we'll do this sort of thing more often going into the future. This will be a dry run for a lot of us to do this sort of thing more often. Daniel is going to be telling us about covariant phase space with boundary. Let me just encourage all of you to mute your microphone. I will be muting my microphone after I finish the introduction. So why don't you mute the microphone. If during the talk you have a burning question during the talk, feel free to unmute and just jump in and ask your question. Otherwise, we'll have questions at the end. We will not be taking the speaker out for dinner tonight.
Oh, come on.
It might be good to mute the videos also.
Yeah, I think most of those are muted.
All right, yeah. Okay, and yeah, so hopefully we'll take him out for dinner when he comes under more standard circumstances. Okay, with that, why don't you take it away, Daniel? I'm muted.
Okay, great. So hi everyone. So when I use this Blackboard software, I can't see any of you. So if somehow you stop hearing me or seeing me or something, you can speak up and I'll hear you. And you know, I like questions. Questions are good. That's kind of the thing that's hard to do over the internet. So I'll try to ask for them fairly regularly. But like Nima said, you can also interrupt me. It can even only be like a somewhat burning question, not like a extremely burning question. Okay, so anyway, thanks for the invitation. Sorry for this weird circumstances we find ourselves in. I'm going to talk about a paper I wrote last year with Jiechang Wu, my postdoc, who is currently trapped in China. Hopefully I'll see him again before he moves on to Santa Barbara, which is where he's going in the fall. So let me start by reminding you just about some of the benefits of Hamiltonian mechanics. Hamiltonian, right? So maybe the best thing about it is it makes the initial value problem simple. And also it makes it easy to do counting of degrees of freedom. Okay, those are the kind of things that the Hamiltonian formalism is really the best at. But in higher energy physics, we actually don't tend to use it that much. And the reason is because it, at least in the standard way of doing it, it breaks covariance. You know, that can be pretty annoying when you're in the middle of doing calculations, and especially like in a theory of gravity, it's very inconvenient. So at least when I was a student, I was kind of under the impression that there wasn't too much you could do about this. Like if you wanted to do the Hamiltonian formulation, you were just stuck picking some Cauchy slice and decomposing the phase space into Q and P, which was where the P was, you know, dl dq dot, with the dot being the time for those slices. And it just seemed to be something that we had to live with. But actually that's not true. And there's an old idea which goes back to, well, I think a long way. So let me say the idea and then I'll discuss the history a little bit. So here's an idea, which is that instead of talking about Q and P, we instead talk about the set of solutions of the equations of motion. Okay. Well, the first place I found this written down, although probably it's not the first place it was discussed, is in some paper by Ed and Chernkovich in 1986. So I don't know if Ed is here, but maybe he knows some earlier reference, but that's the earliest one I know where it's written down. And the idea is pretty simple. It's just that if the initial value problem is well posed, then the set of initial data on a Cauchy slice, which is something like this, basically what this Q and P are parametrizing, should just be the same as the set of solutions. And the set of solutions is a covariant notion. So this is kind of the starting point for trying to do covariant Hamiltonian mechanics, is to kind of make sense of this idea of viewing the phase space as the set of solutions. Is there a question? No? Okay, maybe I just heard some feedback. Now, in order for this to work, you would also need a covariant construction. Someone has, I think, their microphone not muted, and I'm hearing feedback. So you can check, all of you, if your microphone is muted. So you need also a covariant construction, not just of the phase space, but of, hello? I think someone is unmuted, but it's okay. I'll just keep going.
Greg Moore? Greg, oh, Greg, he just muted, sorry.
Okay, all right, no worries. Hi, Greg, welcome. So in addition to a covariant construction of the phase space, which is kind of what you try to get out of defining it as the set of solutions, you also need a covariant construction of omega, the symplectic form, and also the Hamiltonian. That was discussed in this paper of Ed and Trnkovic in examples, but then at least an attempt at a general formulation was given in a series of papers by Lee, Iyer, and Wald, basically like around 1990 to 1995. And so this algorithm that they proposed is called covariant phase space, or the covariant phase space formalism. And it's become kind of a standard thing over the last 20 years. You see it show up in a lot of places, including in discussions of ADS-CFT. But there's a kind of frustrating aspect of this formalism. So there's a problem, which is that CPS, covariant phase space formalism, in the way that it was presented in these papers of Lee, Iyer, and Wald, I'm not sure what the best adjective is here, but let's say it is cavalier about boundary terms. So everything in the papers of Lee and Iyer and Wald is defined to be ambiguous up to adding a total derivative to things that live in the bulk of the theory, or adding boundary terms. They throw away any such term as soon as they see it. But then, although that's also what people do when they're teaching mechanics, it's kind of problematic if you're really trying to show that the objects that you construct obey kind of the axioms of Hamiltonian mechanics. And that's especially true in gravity, because in gravity, the Hamiltonian itself is always going to be a boundary term. And so if you're throwing away boundary terms everywhere, you kind of don't really know whether you're constructing the right Hamiltonian or not. And also the operators, the observables that you like to consider in gravity, are always addressed to the asymptotic boundary in some way to make them diffeomorphism invariant. And so that dressing also is always kind of going to talk to what's going on at the boundary. So if you really want to get this right, you have to deal with the boundary terms, or else kind of on a case-by-case basis, you have to fix them up each time. And that's kind of what is done in these papers is, in particular applications, you kind of futz around and you try to fix up the boundary terms kind of at the end of the calculation. And so that was annoying for me when I was trying to learn the formalism. And yeah, I guess I gather it was difficult for other people also. What Jay-Chak and I kind of set out to do was rethink the formalism in a way that treats the boundary terms systematically. And I would say, for the most part, succeeded. And I'm going to tell you about it today. But before I get into the formalism, let me also say that in particular, we found that actually the expression for the Hamiltonian, which is in Is there a question? Hello? Is someone talking? Hello? Oh, I think someone unmuted again. Okay.
That's tough because when you show develop a deal with
They're hard to deal with. Is that what someone was saying?
Hi, Sasha Polyakov. Can you please mute your microphone?
Oh, I see. Okay.
Thank you.
Great. Thanks to my enforcer there for stepping in. Yeah. So we were able to, develop a version of the formalism which is systematic in the way it treats boundary terms. And moreover, we found that actually, in general, there is a term in the Hamiltonian that was missed in the papers of Iyer and Wald, and most of the follow-up papers as well. There were a few kind of specific applications where people found this term kind of by trying to fix up Iyer and Wald in whatever specific case they were stuttering. But there was, I think, not a general appreciation that indeed the formalism as presented was wrong, in the sense that there was this term that was missing in the Hamiltonian. So as I go through the formalism, you'll see how that term comes out, and also hopefully kind of see how everything in the formalism works. So before I begin, let me just make a couple of comments and then ask for questions about the introduction. So this is pretty much just a formalism talk, which is a bit unusual for me. Usually there's some problem that I'm trying to solve. So let me just say that we got into this because we were trying to do some computations of the algebra of diffeomorphism and variant operators in Joukiev-Teitelbaum gravity. And we're having trouble computing the commutators. And we're trying to do it covariantly. And we kind of traced down our difficulties to some of these ambiguities. So that was kind of our motivation for solving this problem. But that project still isn't done. So today I'm just going to tell you about the formalism, which I think is quite nice. I think, it's, I mean, I feel now much less confused about the Hamiltonian formulation of gravity than I used to. And hopefully by the end, you'll feel something similar. Okay, so let me ask now for questions before I go into the technical part of the talk. No questions? Going once, going twice? Okay, so let's start. So now I'm gonna play with this eraser thing. Actually, it's the fastest thing to do is to do that. Ha, okay. So now let's talk about the general idea. And I'm not gonna try to present the old formalism and then fix it up. I'm just gonna present the formalism that works from the beginning. Okay, if you wanna see the history, you can ask me later or look in the papers. So whenever you're doing Hamiltonian mechanics, right, you have a manifold P, which is the phase space. And then living on P, you have a two form, the symplectic form, which is closed and non-degenerate. Non-degenerate. It's a two form. It's a closed, non-degenerate two form. And the reason why the symplectic form is useful in Hamiltonian mechanics is because then if you're given a function, h, it can be any function from p to the real numbers, we can construct a vector xh such that, let me write the equation and then explain it. So that the gradient of h, and so this is, in this talk, delta is always going to be the exterior derivative on phase space. And that's to distinguish it from the exterior derivative on space-time, which is going to be d. And let me say now, and then because this is going to be a constant thing during the talk, both exterior derivatives are important. Most of the objects we consider will be differential forms, both on phase space and space-time. And so we'll simultaneously be making use of delta and also d. And then this dot here means insert xh into the first argument of omega, okay? So what we're saying here is that the idea is what we use the symplectic form to construct a vector such that if we dot it into the symplectic form, we get the gradient of the Hamiltonian. And this is just Hamilton's equations. And the reason why we want omega to be non-degenerate is because then that makes this, make sure that this xh is going to exist and be unique, right? Because if you like, you can say that xh is just defined to be minus delta h dotted into omega inverse. Okay, and so that constructs for you xh. So that's how you're supposed to think about the symplectic form. It's a machine for turning a function into a vector. And then the evolution is just flow by xh. Okay. So that's just the standard geometric presentation of Hamiltonian mechanics, hopefully familiar to everyone. That's what we're going to aim for. So the goal of this talk is going to be to produce for you this phase space and this symplectic form and this Hamiltonian such that omega is closed and non-degenerate and this Hamilton equation is obeyed. And we want to do that starting from a Lagrangian field theory, and when we want to do it in a way where we preserve covariance at every step. So we never have to pick a frame, we never have to pick a Cauchy slice, anything like that. Okay, let me pause again and ask for questions about this general setup. Okay, going once, going twice. All right, so now let's talk about a field theory. So let's say we have some space-time manifold, M, which I'll take to have a spatial boundary gamma, and then I'll take it to have a future Cauchy slice sigma plus and a past Cauchy slice sigma minus. We'll take the action S to be an integral over M of a Lagrangian density, which depends on two kinds of fields. I'll say what they are in a sec. And then we're also going to allow at the boundary of M a boundary term, which is also going to depend on the two kinds of fields. And the idea is that phi is dynamical and chi is background. So in general, like in the wild, when you meet a Lagrangian, this is usually how you meet it. It comes to you as a function of dynamical and background fields. And then we can think about integrating it to make an action and possibly including boundary terms. So the theory will consist of this action together with boundary conditions for phi. So I'll call the dynamical fields phi a of x on gamma. Okay. So I want to emphasize this right in the beginning that boundary conditions in this talk are imposed at spatial boundaries and not at future and past boundaries. Boundary conditions at future and past boundaries are the things that tell you what state you're considering. They're not the thing that tell you what theory you're considering. But the boundary conditions at spatial infinity, those tell you what theory you're considering. Okay, and then now we're going to follow to construct the Hamiltonian formalism starting from this action and these boundary conditions. We're going to follow a 6-step program. So I'm going to write out the steps now. So step number one, we define configuration space, C tilde, configuration space. Is the set of phi A of X obeying the boundary conditions. Okay, so that's kind of the biggest set of configurations we're going to consider. They don't have to obey the equations of motion or anything else. They just have to obey the boundary conditions. So if we were doing quantum mechanics, this phi A would kind of be this C tilde would be the set of configurations you integrate over in the path integral. In classical mechanics, it's the set of configurations where you consider variations of the action. Okay. So that's step one. Step two, we define P tilde, which is called prephase space. Which is the set of solutions of the equations of motion, where I'll say more precisely what that is, what I mean by that in a minute. And this is a subset of C tilde. So it's they obey the equations of motion and the boundary conditions. Now, before I said that we were going to try to view the phase space as being the set of solutions of equations of motion, but actually that doesn't quite work. I'll explain why not in a minute. So that's why we're calling it the prephase space here. So that's step two. Step three, and this is where most of the details are from the point of view of the Iron, Wald, and Lee formalism, is we define a pre-symplectic form. Which is going to live on P tilde, and I'll tell you how we construct it in a minute. And so this is going to be closed, but maybe degenerate. So this one I'm not insisting on being non-degenerate, and that's how we're going to get the relationship between P tilde and P and omega tilde and omega over here. Okay, so there's most of this talk, I'll be telling you the algorithm for given this L, big L and little l, and given the boundary conditions, how do we construct this omega tilde? Oh, let me also say that technically this is maybe only Greg will care about this comment, but I have to assume that omega tilde has constant rank. Otherwise you can run into global issues. Okay, now that's step three. Step four is I define a symmetry group G, which is contained in the diffs of P tilde, and it's generated by zero modes of omega tilde, okay? So a zero mode of omega tilde is a vector field on P tilde with the property that if you feed it into either argument of omega tilde, you get zero everywhere on P tilde. So that's what I mean by a zero mode. You can show that the commutator of two zero modes is also a zero mode. So that shows that the zero modes of the pre-symplectic form form a Lie algebra. And then you can exponentiate to find this group, which is the action that's generated by the group action is generated by the zero modes. The group elements are generated by the zero modes. You can think, and I'll discuss examples in a bit, but you can think, usually, at least in applications, this G tilde is always associated to gauge symmetries. Let me say also, by the way, that if omega tilde doesn't have any zero modes, then this G tilde is trivial. So in particular, if this omega tilde is non-degenerate, then this G tilde is just the identity. Either way, now, to construct the actual phase space P, we just quotient the prephase space by this group G tilde. And to construct the symplectic form, and I put quotes here, we quotient the presymplectic form by the action of G tilde. Okay, so I put quotes there because this isn't quite literally a quotient in the standard sense. You have to think a little bit about what it means, but I'm not going to get into it in this talk. If you think about it for 5 minutes, it means what you think. And then finally, let me write step 6, and then we'll discuss how to go through this in more detail. If we're given a space-time diff generator, C mu, we want to construct the Hamiltonian HC such that Hamilton's equation is satisfied. So dH psi equals minus, well, actually, let me write it later because I'll have to define a symbol now that I don't want to define until later. So we'll construct the Hamiltonian. Let me now try to explain why we need this distinction between P tilde and P. So it's easy to see already in classical electromagnetism. So if you think about classical electromagnetism, so solutions of the equations of motion, meaning gauge potentials A mu, are not actually in one-to-one correspondence with gauge invariant initial data, because you can do a gauge transformation that vanishes in a neighborhood of a Cauchy slice, but doesn't vanish elsewhere. And that gives you another solution, which on the Cauchy slice is exactly the same, and so has the same initial data. So if you want to hope to get a good initial value problem, you have to quotient by the set of solutions by at least some of the gauge transformations. And the ones that you have to quotient by turn out to be precisely the ones which correspond to zero modes of this presymplectic form. Okay. So that's the general idea. And I now want to stop, and I really want to encourage people to ask questions. So I'm going to wait 20 seconds for anyone who has a question to ask.
Daniel.
Yeah, who is this? Greg?
Greg.
Yeah, that's what I thought. Okay.
Is your action first order in derivatives of space-time or higher order?
Oh yeah, let me comment on that. So I allow any finite number of derivatives.
But it makes a difference whether it's only first. So in general, of course, it's bigger than first order, but the story is different. It's different.
No.
First order.
Here it's not. So here, the formalism I'm going to present doesn't care about that. It works for arbitrary but finite numbers of derivatives. I mean, in principle, it should work for infinite number, except then it might be non-local. So that's why I'm saying finite. So you'll see. I'm never going to have to talk about canonical momenta. So I'm never going to have to care about the number of derivatives. Any other questions? Comments? Okay, I'm gonna delete this screen. Actually, let me erase the left half and let me keep the steps just for a sec, and then I'll erase it in a minute. So. This is a little bit slower, but this way we can keep the steps up there just for a little bit longer. Okay, so now let's talk about how to construct omega tilde and the Hamiltonian HC. So our guiding principle from which everything is going to follow is that we will only view the action, principle. So I got to switch back away from the eraser. The action is well posed, means that phi obeys the equations of motion if and only if S is stationary up to future past terms at phi. So let me again comment on that. So I said I'm not going to impose boundary conditions at the future and past boundaries. Let me draw that picture again over here. So I had sigma minus and sigma plus, and here's the spatial boundary gamma, and here's M. So when I look at the variation of the action, I allow for boundary terms at future infinity and past infinity, because since I'm not imposing any boundary conditions there, there's going to have to be boundary terms there. But I'm not allowing boundary terms at spatial infinity gamma, okay? So let's see what that means. So we can compute the variation of the action. To do that, it's convenient to first compute the variation of the Lagrangian. So let me remind you that in my action, maybe I'll write it again up here, S is equal to the integral over M of L plus the integral over the boundary of M of little l. So for me, and this is a trick from Ironwald, I'm always going to think of the Lagrangian as a D-form, not as a scalar. So you can take the Lagrangian density and multiply it by the volume form, and that gives you this capital L. Now, if we look at the variation of L, by doing integrations by parts, you can always write it into something which is proportional to the variations of the dynamical fields, not with any derivatives, plus the exterior derivative of something which is called the symplectic potential. So for any local action which is constructed covariantly out of dynamical and background fields, you can always extract this theta by just kind of doing integrations by parts without the integrations by parts. I'll show an example of that in a sec. So then if we compute the variation of the action, we have an integral over the interior of the space of EA delta phi A plus an integral over sigma plus minus of this theta plus delta L plus an integral over the spatial boundary of theta plus delta L, where you see we just use Stokes' theorem to move the d theta sitting in the variation of L out to the boundaries here and here. Now, stationarity tells us, one, that since we can consider variations in the interior that vanish near the boundary, we need to have EA equals 0 everywhere. This is the equations of motion. But then we also need to say something about this term, because if this term were really here, then the action wouldn't be stationary up to terms that live in the future and the past, because there'd be additional boundary terms sitting here at spatial infinity. So to avoid that, we need that theta plus the variation of the boundary term evaluated at spatial infinity to be equal to, well, now you might think 0, but actually it doesn't need to be 0, it just needs to be d of something. And I'll call this something c, because you see if it's d of something, then I can use Stokes' theorem to push the integral over dc up into the corners here, up and down into the corners here, and those are still part of the future and the past. And this is like the most important equation for us. We're gonna like be using this equation constantly. So let me put a box around it and let me also put a star, okay, to make sure we appreciate this equation. This equation, if you like, is kind of a consistency condition on the boundary conditions and the choice of this boundary term little l. If we somehow we pick the boundary conditions and we pick little l and this is not true, then it means that the action formulation is not well posed and we have to think more and come up with a different boundary term or figure out why our boundary conditions were inconsistent. And so we're going to impose this equation from now on. So any questions about this, or I'll quickly do an example. Actually, I'll do 2 examples. All right, 10 seconds. All right, so let's just quickly do a couple of examples. And let me also pay attention to the time here, okay. So the first example I'll consider is the obvious one. I'll take L to be -1/2 d mu phi, d nu phi, g mu nu times the volume form. So this is just a free massless scalar field. So you see this already, it has a dynamical field phi and it has a background field g mu nu, which also shows up inside of the volume form. So if we compute the variation of the action, or of the Lagrangian density, what you find is that this theta is equal to minus d mu phi, delta phi, dotted into the epsilon tensor, where again, I remember the dot means you insert it into the first argument of the epsilon tensor. So in particular, if you evaluate theta on the spatial boundary, what you get is minus n mu d mu phi delta phi times epsilon on the boundary of the volume form for the boundary. So let's think about this from the point of view of this equation. So here if I set little l equals to 0, then I don't have this. And so then I need this to either be a total derivative or I need it to just be 0 on the boundary. And you see I can accomplish that in two simple ways, right? I can set this equal to 0, which is Neumann boundary conditions, or I could set this equal to 0, and that's Dirichlet boundary conditions. So either the choice of Dirichlet boundary condition or the choice of Neumann boundary condition allows for this star equation to be satisfied with L and C both equal to 0. So we don't need an L or a C in this example, okay? And if we somehow had chosen anyway to add some L that messed this up, then we would have destroyed the well-posedness of the action, and then we would have had to take that away or change the boundary conditions. All right, any questions about the example? All right, I want to do one more example, just to make sure we're all on the same page, and also because it's nice to have an example where little l and c are not 0. So the other example I'll consider is general relativity, where I take L to be 1/16 pi g times r minus 2 lambda times epsilon. I take little l to be 1/8 pi g times the extrinsic curvature times the volume form on the boundary. So that is the Gibbons-Hawking term. And then you can do a little calculation, which I'll spare you the details of. You can compute the variation of theta plus delta L evaluated on the spatial boundary. And what you find is minus 1/16 pi j, k mu nu minus k gamma mu nu, where this is the induced metric on the boundary, delta g mu nu plus dc, where now c is equal to minus 1/16 pi j, gamma mu nu and alpha dg nu alpha, dotted into the epsilon tensor on the boundary. So this is an example where c is not 0. So, and in fact, you see that in order for this equation to be true, we want this first term to vanish. And there are two ways that we can do that. We can take the variation of the pullback of the metric to the boundary to be 0. So that's Dirichlet boundary conditions, like that's what we usually do in ADS-CFT. We only need to fix the pullback because this thing is contracted with tensors whose indices live only on the boundary. This is the extrinsic curvature and the induced metric. So we can either fix the pullback of the metric to the spatial boundary, that's Dirichlet, or we can fix this combination of extrinsic curvatures to be 0, that's like Neumann. And you might recognize this, and we'll comment at the end if we have time. This is basically the Brown-York stress tensor sitting here. So that's like setting the Brown-York tensor to 0 to infinity. That's Neumann conditions for gravity. For either of those choices, this term is gone, and then we see that the Start equation is satisfied. So we've succeeded in writing an action formulation for gravity with a boundary. and in fact, that's kind of why Gibbons and Hawking came up with this term in the first place. Okay, so any questions about these examples? Wait 10 seconds. Okay. Now I want to make a little table here just to clarify something, because I introduced a bunch of symbols here, and this theta and this C and everybody we're going to interpret as I said before, as differential forms both on space-time and on phase space, or let's start on configuration space on the set of all phi obeying the boundary conditions. So let me just explain how that works. So I'm going to make a table where I give the space-time and the C tilde ranks of these various objects. So L, the Lagrangian, is a D form on space-time and a 0 form on configuration space. Little l is a D-1 form on space-time and a 0 form on configuration space. Theta is a D-1 form on space-time and a 1 form on configuration space. So let me remind you of that, right? Theta showed up in this equation. So you see it's got a variation of phi sitting inside of here. But remember, for us, when we write this symbol delta, we don't actually mean a variation. We mean an exterior derivative on configuration space. So for example, as you see here, this theta has a delta in it, right? And this theta over here, well, it has mixed with the delta L, but it also has a delta in it. So since it has one delta sitting inside of it, it's a 1 form on configuration space. C is a D-2 form on space-time, you see, because D of it is a 1 form. And it's also a 1 form on configuration space. And then I'll leave a gap here for the thing I'm going to define in a moment, which will end up being a 2 form on configuration space. Okay, so it's good to always keep track of these different kinds of differential form indices. Okay, I can take more questions while I'm erasing the left-hand side here, if there are any. Okay, so we're now in a position where we can try to define the presymplectic form, which was the goal of our STEP program, which I've unfortunately had to erase because the software is not great. Thanks, Microsoft. So what I want to do is now I want to define a new object, which is called the presymplectic current. Which I'm going to define to be the configuration space exterior derivative of theta minus dc pulled back to prephase space, which is the set of solutions of the equations of motion. So just to remind you, let me write the two equations up here. Delta L is EA delta phi A plus dc, and theta plus delta L restricted to gamma is equal to dc. Oh, sorry, this is d theta here. Okay, this was just the definitions of c and theta. So this is a proposal for an object omega, which we can now see is a D-1 form on space-time and a 2 form on configuration space, because you see it's the exterior derivative of a 1 form on configuration space. So let me also say this is the first point where we're going to differ from Eyre and Wald, because they wouldn't have written this second term here. And you'll see in a moment why that second term is important. Now, there are some nice properties of this omega. Let me say what they are. There's an obvious one, which is that delta of omega is 0. So omega is a closed form, closed 2 form on configuration space.
Sorry, why omega is not 0 in the first place? Like, isn't
Why omega is
theta
not zero?
yeah,
Because,
isn't theta minus dc just delta L small?
yeah, but that's true only on the spatial boundary, whereas this lives throughout the space-time. That's actually going to be our property number 3, is that omega is 0 on the spatial boundary.
Oh, sorry. How do you extend C?
Good,
So
good,
C is
yeah,
somehow...
so good. So I extend C in an arbitrary way into the space-time. It doesn't
Okay.
matter. Yeah,
Okay,
good
thanks.
point. Yeah, I was going to say that later, but thanks for bringing it up. Okay, so delta omega is 0. So that's easy. More interesting is to compute d of omega. So let's look at that. So the first comment to make is that delta and d are commuting exterior derivatives. So like maybe this can be called like a commuting bicomplex or something for people who like such things. So in particular, that means that d of the second term is going to vanish because I can move the space-time d outside and then it hits it. And moreover, since d and delta are commuting, this is equal to delta of d theta.
Excuse me, Dan. The
Yes.
second term was only defined on the boundary?
Yeah, that was the same question as before. So I take the C, which I get on the boundary, and I extend it arbitrarily into the bulk, however I like. But you're going to see in a minute that we're only going to care about the value of C on the boundary. Okay? Okay, so let's keep computing d of omega. So I can use, remember d theta shows up over here, right? So I can write this as delta of delta L minus EA delta phi A. And so delta squared is 0, so I can write this as minus delta EA wedge delta phi A. But that's 0 because we're pulling back to prephase space, and on prephase space, E is 0 everywhere. So the pullback of its gradient is also 0 everywhere. So we've learned that omega is closed both as a 2 form on C tilde and as a d-1 form on space-time. And then finally, this is the comment that someone made before. We can check that the restriction of omega to the spatial boundary is equal to the variation or the exterior derivative of theta plus delta L minus dc evaluated at the spatial boundary, but that's 0 by our favorite equation up here, okay? So, so the pullback of omega to the boundary is 0. So these are the 3 essential properties of omega. And the reason why we like that, these 3 properties, is because now we can define the presymplectic form, omega tilde, to just be the integral over any Cauchy slice that we like. I'll call it sigma of omega. So let me put a box around this. This is our covariant construction of the symplectic form. So let me just comment on its properties. It's closed as a 2 form on configuration space or on prephase space. That's because omega is closed, and so doing an integral over space-time doesn't change this from being closed. And actually, it's also independent of our choice of sigma. And that follows from these second 2 properties. So maybe let me just quickly draw a picture. I won't fill in the details. So say here are 2 Cauchy slices, sigma prime and sigma. The integral of omega over sigma prime minus the integral of omega over sigma is just equal by Stokes' theorem to the integral of d omega everywhere inside, plus some flux terms at infinity, but those all vanish by these conditions 2 and 3. So this omega tilde is indeed independent of the slice and closed. So it's a good candidate for a presymplectic form. All right, and in fact, that's what we're going to take as the construction of the presymplectic form. And let me emphasize that because of the C that we added here, which by the way, you see here is just going to contribute a boundary term in the presymplectic form, the presymplectic form we get is different from the one of Eyre and Wald because they did not include the C here. And that's going to lead to the difference we have with them over the form of the Hamiltonian. All right, so that's it for constructing the presymplectic form. Let me stop and ask for questions again. I'll wait 10 seconds.
Did they instead include C as a boundary contribution in the definition of capital omega?
No, they just didn't mention it at all. They said that, well, what they said was that they said that there could be boundary terms in omega tilde, but they hope not.
Okay.
Yeah. that's not quite literally what they said, but it's basically what they said, and I don't think Wald would argue with that. Let me say also, by the way, that we had, just as a sociological comment, so, you know, back in, you know, the time where things were nice, we had Wald come visit, maybe, I guess last spring maybe, and we talked for a long time, like 10 hours, and I think he agrees with everything I'm saying here, so I'm not misrepresenting him, misrepresenting things when I say that this is a term that they didn't have. Okay, any other questions? Okay, I'm going to erase this half now here, and we can proceed to constructing the Hamiltonian. Okay, now, so now we have prephase space, we have a presymplectic form. We can look at the zero modes of the presymplectic form, and we can quotient by them, and that constructs for us the phase space and the symplectic form. But to declare victory, we also need to find the Hamiltonian. So let's talk about that. So in order to ask for a Hamiltonian, we first have to think about what we're really asking for. So somehow the Hamiltonian should be a generator of diffeomorphisms of the theory, but not just any old diffeomorphisms are allowed, because in particular, right, like for example, the metric might not be dynamical, and if the metric is not dynamical, then most diffeomorphisms aren't going to be symmetries. So that's one thing we could worry about. We could also worry about, since we have boundary conditions, the diffeomorphisms had better respect the boundary conditions. If they don't, then those also aren't going to be symmetries, and it wouldn't make sense to try to write down a Hamiltonian for them. So what we're going to consider are diffeomorphism generators xi mu, such that one, xi mu preserves the boundary conditions. Is someone not muted? Okay, there we go. Good. So xi mu preserves the boundary conditions. That's requirement number one, or more accurately, the diffeomorphisms that it generates preserve the boundary conditions. I hope that's not me. Is that me?
No.
Okay.
I think there's a user 5ZKQ/long name is needs to mute their microphone.
Nima, you can do it by force, by the way, if you, since
can
you're the
I?
host.
Hold on.
Yeah, I think you can.
Well, let's see. I think maybe our media technology.
Oh, maybe Dario is the host. Then Dario
maybe
can
Dario's
do it by force.
got to do it.
Yeah. Okay.
There's user 5 is needs to be muted.
I see. By the way, you know, Zoom has a feature where the host can also see whether people have the video on their top screen or not. I don't know whether that's a good feature or bad feature. Okay, so we're interested in a diffeomorphism that preserves the boundary conditions, but not only that, we also want that the Lagrangian and the boundary Lagrangian are covariant with respect to xi mu, and thus also the same for theta and c. So this is basically saying that let me say what I mean by covariant, and then I'll be more clear what I mean by this. So let's say we have a space-time tensor sigma, which is built out of both the dynamical and the background fields. So the diffeomorphism transformation of sigma is that we just take the Lie derivative of sigma with respect to xi. But when we do it, we have to act both on the dynamical and the background fields. But symmetries are not allowed to act on background fields, right? Things that act on background fields don't necessarily give you conserved quantities and so on. So what we really want is that if we act with the diffeomorphism only on the dynamical fields, this quantity sigma still transforms like a tensor. Okay, that's the sense in which we say it's covariant, and that's what we're saying up here about big L and little l. If that's not true, then we don't expect to have a symmetry. And so let me just comment that, so you can prove that if big L is covariant, theta is also covariant. With C, it's a little bit more technical, but roughly speaking, if little l is covariant, then C should also be covariant. But rather than try to argue that, I'm just going to assume it. So I'm going to assume that big L, little l, theta, and C are all covariant. Now I can define covariance in a slightly nicer way. What I'll say, I can do that by defining a vector field, xc, on configuration space. And I define it to just be the integral over all of space-time of the Lie derivative of each of the dynamical fields contracted with the partial derivative operators on configuration space. So this is the vector field on configuration space whose flow, the flow it generates, is just the infinitesimal diffeomorphism generated by Xi on all of the dynamical fields. And the reason that this is nice is because then covariance is just saying that the Lie derivative of sigma with respect to xc as a vector field on configuration space is equal to the Lie derivative with respect to xc, where you view sigma as a tensor on space-time. So this is going to be our definition of an object being covariant. And so in order to have a symmetry, we want big L, little l, theta, and C to all be covariant in the sense that they obey this equation. So in other words, they transform as tensors even if you only transform the dynamical fields and not the background fields. Okay, any questions about that? 10 seconds? Or I'll start erasing the other side here so you have a little more time.
So if we had a system whose Hamiltonian is time dependent, would this work or not?
No, so yeah, the formalism I'm setting up now would not work for that. I think you can probably extend it to discuss that. Yeah, here I'm kind of restricting the situations where the Hamiltonian that we get will be conserved and so on. Yes. Yeah, probably you can do it. I just, somehow it was, we were lazy and we didn't try to do that. Okay. All right, so now here's our goal, is that we want to find HC such that the exterior derivative of HC is equal to minus the insertion of this vector XC into the presymplectic form. Okay? So this was Hamilton's equations that I wrote down before. So if we can find some H such that this is true, then you see XC by definition, right, is the vector that corresponds to implementing the diff on the dynamical field. So if we can find an H obeying this equation, then by definition, this H generates the diffeomorphism. So we've succeeded in finding an H. And so our goal is just going to be, so what we're going to do is we're just going to compute the right-hand side here. And then we're going to see that by being clever, we can show that it's equal to delta of something. And then we can declare victory and see what the something is and declare victory. So in doing that, there are two convenient things I want to mention before I compute the right-hand side here. So the first is just a definition. So there's something JC, which is called the Noether current. Which is defined to be the insertion of XC into theta minus C inserted into the Lagrangian form. So, so here now again for this dot, right? This dot always denotes the insertion of a vector into a differential form. And you can tell by looking at the vector whether it's a configuration space vector or a space-time vector. That tells you kind of which kind of index to insert it into on these differential forms. Okay, so that's just a definition. Then we're also going to make constant use of Cartan's wonderful formula. So let me write Cartan's formula just in case you don't remember it. It says that the Lie derivative with respect to a vector of a differential form omega is equal to, so now we have to pick which kind of exterior derivative to write. I'll write the space-time ones. It's equal to d of that vector inserted into the first argument of the differential form, plus that vector inserted into d of the differential form. So this is Cartan's magic formula. It tells you how to compute the Lie derivative of a differential form with respect to a vector field. Okay, now we're going to just compute the right-hand side here and see what we get. So let me just ask before then, any other questions? Okay, so I'm going to start by computing the insertion of xc into the presymplectic current omega. So let me remind you that that was defined as delta of theta minus dc. Okay, and this was restricted to prephase space, but I won't write that down. We can first write this. So the thing to notice is that if you have a vector dotted into d of a differential form, that's like this term here in Cartan's formula. So I can rewrite this as the Lie derivative with respect to xc of theta minus delta of xc inserted into theta. So that's this first term. And then the second term, I can do the same thing. So pulling the d outside, I can write this as the Lie derivative of c with respect to xc minus delta of xc dot c. Now let me make a barrier here, so make sure it doesn't get out of control. Now, using the covariance of theta, I can write the first term as L little c of theta instead of L x c of theta. That's where I use that theta is covariant. And then I can expand that out using Cartan's formula, but now for space-time indices. So then I'm going to get c dot d theta plus d of c dot theta. That's this term. Then this term, I can rewrite using the Noether current here, right? Because xc dot theta is part of the Noether current. So I call this minus delta jxc minus c dot delta L. And for now, I'll just keep this term as is. So I'll write minus d of stuff. Now, this d theta, remember that the variation of L was equal to EA delta phi A plus d theta. So I can replace d theta by delta L minus EA delta phi A. But since we're living in prephase space, EA is 0. So I can just write this as delta L. And then you see this term is going to cancel this term, which is wonderful. And we're left with minus delta jxc minus d of minus c dot theta plus lxc of c minus delta of xc dot c. All right. So I apologize for doing this calculation, but I thought it's kind of fun to see all this technology at work. This is the only calculation that I'm going to do, and we're already halfway there. Okay. Now, to get the rest of the way there right now, we want to compute minus xc inserted into the presymplectic form. So we want to minus all of this and then integrate it over space, over a Cauchy slice. So therefore, omega, let me undo that. So minus xc dot omega tilde is equal to the variation of the integral over the Cauchy slice of jxc. So that's good. That's already delta of something, you see, which is what we want. Then I can write it as plus an integral over the boundary of the Cauchy slice of a bunch of stuff. So we get minus xi dot theta. Let me think how I want to say this. Yeah, let me do it like this. So I get minus xi dot theta. Now here I can use the covariance of C. So C, as we extended it into the interior of the space, might not have been covariant, and in fact usually won't be. But now, since we use the total derivative, we're doing everything at the boundary. So C is covariant. So I can write this as L xi of C, which is just xi dot dc plus d of xi dot c. But the d of something, since this delta theta is a closed manifold, it's going to integrate to 0. So I can just replace this by that. And then I get minus delta of xc dot c. Okay? But you see, now here we're in good shape because we can write this as xi dot dc minus theta, which I want to remind you of our favorite equation, theta plus delta L is equal to dc, right? This is just delta L. So now you see, now we've succeeded. We've ended up with delta of the integral over the Cauchy slice jxc plus the integral over the boundary of the Cauchy slice of xi dot delta L minus xc dot c. So let me put a box around this. Actually, I think what I'll do instead is I'm going to erase over here. Okay, so we've learned that we can take hc to be the integral over space of jxc plus the integral over the boundary of space of xi dot L minus xc dot c. Now, let me emphasize that here I only had to assume that the various quantities were covariant under xi. So I could apply this, for example, like in quantum field theory, you know, xi could be a boost or a rotation or a translation, and this derivation would have been correct. We might not have called, if it were rotation, we might have called this the angular momentum, or actually minus the angular momentum instead of the Hamiltonian. But we can apply this for any xi, which is a symmetry of the theory. But the situation is especially nice if we're studying something which is generally covariant, like general relativity. So if L, etc., are covariant under arbitrary xi mu, or in general xi mu that preserve the boundary conditions, then it was shown by Iron-Wald that g xi is always equal to d of something called q xi, which they very unfortunately, and it's really Wald to blame, I think, called the Noether charge. So this is a terrible name, right? It's clearly hc is the Noether charge, right? So if I were Wald, I would have called this the Noether potential or something. But anyways, probably we're stuck with the name. Anyway, so there's this qc. And so in covariant theories, generally covariant theories, that means that we can write the entire Hamiltonian as a boundary term, qc plus xi dot L minus xc dot c. All right. And so you see explicitly, right, this kind of shows you that the generators of diffs in, say, gravity theory are always going to be boundary terms. So let me stop and now ask for questions about this. And then after this, what I'll do is maybe I'll just show you what these look like for general relativity, and then we can be done. I don't want to go on for too long. So let me first stop and ask for questions.
So Iron-Wald, I think, had an experimental check of this relationship, right, between JC and DQ, like they constructed it for various theories. Is there a way to see that this should be true?
I guess I didn't know about what you're talking about. That's interesting. Sorry, an experimental.
Experimental in the sense that they constructed it in the various theories that JC was equal to.
Yeah, that's right. Yeah. I'm going to do that in a minute also. Yes. Okay. So they did. That's right. Oh yeah. Let me mention, by the way, right. So let me comment on how this is related to what Iyer and Wald did. So the formula they wrote. So the term they're missing is this term involving the C, because they didn't put the C into the presymplectic form. And then this first term also they didn't explicitly have because they just didn't include boundary terms in the action. And this L for us is defined as the boundary term in the action. But what they found is that when they tried to satisfy Hamilton's equation with their presymplectic form missing the C, it didn't work unless they assumed some kind of integrability condition about theta, so then they just guessed that basically theta at the boundary must be equal to delta of something. And let me put a minus sign, let me undo that. They just assumed that theta at the boundary must be equal to delta of something they called B. And so then this L here for them is minus their B. So if you set C equals 0 and you set L equals to this minus this B, you recover the formula for the Hamiltonian that they wrote. And the reason why they didn't get into trouble is because in the examples that they happened to check, this C turns out to be 0, basically by kind of a lucky choice of gauge. So I don't know, does that answer the question, Juan?
No, I was just asking about the derivation of why, for a general covariant theory, J psi is equal to D cube psi.
Oh, about that derivation, yes. Yeah, I think that derivation is correct. I mean, that doesn't involve boundary terms, right? You're just looking at it's just a property of the action, of the Lagrangian density. So I'm using their derivation here. I'm using Iyer and Wald. I'm going to tell you what Q is in general relativity. I don't know if that's what you're asking.
That's okay. Yeah.
Okay. All right. Any other questions about this, or I'm going to then just discuss GR and then maybe we can be done for the day. Okay. Then let me erase this derivation over here. If you want to look at it again, it's in our paper, of course. And we also do many more examples. We do lots of examples in the paper. I just don't have time to do too many here. Okay, so let me now discuss general relativity. So let me remind you that in general relativity, we had L was 1 over 16 pi g times r minus 2 lambda times the volume form. We had little l was equal to 1 over 8 pi g k times the volume form on the boundary. And then, well, that'll be enough to go on for now. So then you can, you can work out what is theta and what is C and so on. And what you find is that this Q, C, is equal to minus 1 over 16 pi g times star d C, where C, this is where you lower the index on C and view it as a one form. So I won't go through all the algebra here, but you can check the D of this gives you the JC, which is the JC you find using the formulas I wrote before for general relativity. Now, to compute the Hamiltonian, I need a few more things, so let me just say what they are. So first, I need to evaluate QC I need to restrict it to the boundary of a Cauchy slice. So if you do that, then you get 1 over 16 pi g times tau beta n alpha minus tau alpha n beta times d alpha c beta times the volume form on the boundary of the slice, where let me say now, so this tau is the normal vector to the partial of sigma viewed as part of the boundary. So here's the this dot here, these dots are partial sigma. They have a normal vector inside of the boundary, and that normal vector is tau. This n alpha is the normal vector of the boundary viewed as the boundary of space, okay? And so when you take this formula and you pull it back to this delta sigma, you find that this is what Q is. Similarly, you find that C dot L, evaluated on the boundary, is equal to minus 1/8 pi g tau alpha Xi alpha times K times the volume form on the boundary of the Cauchy slice. And then finally, this xc dot c term evaluated on the boundary of the Cauchy slice, you find is 1/16 pi g times tau alpha and beta plus tau beta and alpha del alpha c beta epsilon evaluated on the partial of c. So that's just some algebra to check. You can check it yourself, or you can look in our paper if you have trouble checking it. But just churning through the crank. And you see everything here looks covariant, right? I've written everything in terms of space-time tensors. Okay, so now let's compute the Hamiltonian. So I'll write it as minus 1/8 pi g integral over sigma. So you see by combining, so we see we have qc minus xc dot c. So half of these terms are going to cancel and the others are going to combine. So you get tau alpha and beta del alpha c beta from those two terms. And then from the Gibbons-Hawking term, the extrinsic curvature term, you get plus tau alpha c alpha times k, and then all times the volume form integrated over the boundary of the Cauchy slice. Now, this I can simplify using, let me write it over here, that c beta n beta equals 0. So let me remind you, so xi is our diffeomorphism, n beta is the normal vector from the boundary. So this is saying that the diffeomorphism respects the boundary conditions. It can't, at the boundary, the diffeomorphism can't have a normal component, because if it did, that would move the boundary around and it would violate the boundary conditions. So then that means that we can replace this by minus xi beta d alpha and beta. And this is then just the extrinsic curvature, k alpha beta. So what we find is minus 1/8 pi g integral partial sigma tau alpha and beta k alpha beta with a minus sign plus k gamma alpha beta, where this is the induced metric on the boundary. But this is nothing but the Brown-York tensor. So this is minus integral del sigma t Brown-York alpha beta contracted with tau alpha and c beta, which is the formula that you want. So this is like the standard formula for a diff generator and general relativity with a boundary. Use the Brown-York tensor. You can specialize this, for example, if you're in asymptotically ADS or if you're in asymptotically flat space, then you can stick in non-covariant representations of these quantities, and you can just recover the standard kind of ADM Hamiltonian. It's a few more lines of algebra. So I really want to emphasize, like, this is actually really easy, what I just did here. Like, I mean, you have to churn out these things, but it's not that hard to churn these out, starting from these expressions for the Lagrangian and the boundary Lagrangian. And then it's just, a couple lines of algebra to get to the Brown-York tensor. If you try to do this using standard techniques like non-covariant techniques, it's pages of algebra. And we do some of the pages of algebra on the appendix to our paper so that you can see what this looks like if you try to do a 3+1 decomposition and introduce canonical momenta and do a canonical transformation, do the Legendre transformation, and so on. And that's maybe what I want to be the takeaway for this is not, the formalism is nice, but this is also very suited to practical computations. I mean, you see, using the tools that I was kind of demonstrating during this talk, there are all sorts of things that are just really easy. Like another thing, for example, I want to know the Hamiltonian for the Schwarzian theory, which is something that people think about. Oh, it's some higher derivative theory and so on, but you can just run it through this machine and it's a couple lines and you get out the right formula for the Hamiltonian. So, there are other things you can do with this, obviously. I mean, as I said, our motivation was doing some computations in Joukiev-Teitelbaum gravity, which we're still doing. But this formalism has really been helping us a lot doing them. And, I can imagine that hopefully it'll become kind of a standard thing in the future. So, okay, let me stop there. I think we've gone on long enough. Thanks. Thanks, Nima. I appreciate it.
Thank you very, very much, Daniel.